Hi guys, glad you can make it in such great numbers. I want to take you on a small journey into the depths of SOC and how we try to improve them, because right now we have a couple problems with them. And part of that is what I like to call SSA CFG Yul, and the title is kind of a bit of a double title, at least the subtitle. A new viaIR backend, as in we take the viaIR pipeline and slap on a new stage after it, but in reality it is also a new IR backend. And I will tell you what that means really in a second. To give you a bit of motivation and background, I first want to have a look at the performance of viaIR right now. And with performance, I don't mean bytecode performance, because you could talk about, deployment gas, you could talk about runtime gas, but what I mean really is how long does it take to invoke the compiler performance? And that's not ideal at the moment with viaIR. And we're going to look into that. So a little bit of history. Yeah, this is probably very small, but at the bottom left of that graph, there is the version 0818 that was beginning of 2023. And back then, we compiled, for instance, eigenlayer, which now compiles at 4.4 minutes on my home machine at about half an hour. So we already came quite a way. So that's a reduction by 80%. But still, 4.4 minutes is 4.4 minutes, right? You don't want to wait 4.4 minutes until your project compiles. So we have to do something about that. This is just a selection of projects. So we have eigenlayer, OpenZeppelin, and I think I even squeezed in Uniswap there into the graph. But we can also make use of our friends on Sourcify, right? Sourcify has this really nice database that you can download to your little home machine and then play with it. And that's precisely what I did. I took the Sourcify database, wrote a little SQL query down there, pulled out about 6,000 contracts, compiled them, and just checked out how long does this thing take? How much time do I need? And it turns out many contracts are quite fast to compile. Some of them are relatively slow, so you can see like it's a logarithmic X scale, so this goes up to 10 to the 2 seconds, so we are in the minutes regime at the tail end, but it's also not the whole story, because for the projects that take really a long time to compile are the ones that also have a lot of testing, and ideally you would want to have a lot of testing, and compiling these tests into SOC is then another aspect of it that is very time intensive. Still, this is only an outside view. Yeah? We want to dig deep. And to dig deep, we have to look at what does SOC do, actually. And if you invoke SOC, and let's ignore the standard JSON stuff for a second, but just use the ordinary CLI, then we can do SOC --viaIR. So we will take Solidity code, transform it to Yul, and then --optimize. So there's going to be a Yul optimizer, and then we have maybe a couple more arguments, which I just denoted as star args. And then what happens with these sources is it goes into what we call the compiler stack. It will produce Yul, go into the Yul stack. Yul is our IR right now, and this Yul stack will then just parse and analyze the generated Yul, optimize it, assemble it. Then we have another optimization stage after the code transform. So the code transform is what transforms the stack layout, so the stackified code, to EVM bytecode. And on top of that, we have another optimization stage just purely on the assembly, which is assembly optimize. And then in the end, we have the resulting bytecode. If you look at a couple of these steps, you can see the ASM optimizer, ASM short for assembly, is relatively quick. So is the code transform. So whenever I say code transform now, I mean the stage that transforms stack layouts, so stackified code, to EVM bytecode. That is also relatively quick. And what takes a majority of the time is the Yul optimizer. So we certainly have a lot of work to do. And how do you want to read this graph, right? This is over the 6,000 contracts we pulled out of Sourcify, and each of these contracts is then sorted into bins. So it's kind of the time distribution over these 6,000 contracts. So let's look at the Yul optimizer. What can we learn? And what I did is I looked at eigenlayer, because it takes a long time to compile, and I wanted to figure out why does it take so long, right? Where are we stuck? And turns out it really depends on the structure of the input. And if you take a project like eigenlayer, that is not really just one contract, right? But it's a collection of contracts. It's, I don't know, correct me if I'm wrong, but it's probably something like 120, a little bit less, I think. And each of these 120 contracts has a different structure, has a different AST, so abstract syntax tree, that's kind of the data representation of the code. And based on that, you get different results. So here I cherry-picked something, and this shows that a lot of time is spent, for instance, in common sub-expression elimination. That's like the topmost bar. Common sub-expression elimination is something that strongly depends on data flow analysis, because you have to kind of track which variable has for how long which value, and then if you want to substitute something, I mean, Nick already mentioned how that works earlier, then you have to make use of that sort of information, which is kind of tough to compute. So here we have an algorithmical problem. But if we look deeper over all of these 120, let's say, contracts, we see DFA standing for data flow analysis. So DFA-dependent steps cumulatively take actually less time than steps in the optimizer that are not dependent on the data flow analysis part. So we kind of have two orthogonal problems here. One is we have an algorithmic thing to solve. We want to get better at data flow analysis. And the other thing is we just have a slow implementation, and we need to get better at that and get better data structures, think more about the algorithms, how we implement them, do profiling, that kind of stuff. So you can compile your projects more quickly. So summing up, eigenlayer takes about 5 minutes to compile, a little bit less on my machine. And the bottleneck inside the optimizer strongly depends on what kind of AST we're looking at. So that's kind of the gist of it. What can we do? We can look at the SSA form. SSA stands for static single assignment, and I will introduce that in a second, and this SSA form will enable us to alleviate these algorithmic problems and essentially make the data flow dependent steps O of 1, so kind of immediate. At the same time, going to this new IR backend, we have the opportunity to rework and carefully profile a lot of the existing optimizer steps and reframe them in this new IR. So we plan to slowly bring over the current Yul optimizer into the SSA CFG form, and then based on that, really get performance boosts. And what is also nice, it enables us to have better algorithms for code generation, which are easier to maintain and fix, which is good for everybody. And we can also tackle stack to deep, which is something that Alejandro will talk about in the next talk. So I won't go into too much detail here. Okay, so what is SSA CFG? The SSA CFG is comprised of one part SSA. So here we have on the left-hand side something that is not SSA. We have a variable y, which is reassigned from 1 to 2, and then assigned to x. So SSA means each variable, once it is assigned, is constant, which means here we have to introduce more variables. So we only get that at the expense of more variables, but we can make v1 equal to 1, v2 equal to 2, and then v3 corresponding to x on the left-hand side equal to v2. And in that setting, everything is constant, which means if I query my control flow graph or my program, when is something set to a certain value, then the answer is trivial, right? Because once it is set, it is constant, it doesn't change. This kind of approach is used in many state-of-the-art compilers, among them LLVM, GCC, GSLang. And yeah, I already said that data flow-based optimizations are going to be more efficient, which is one of the pieces. And then the CFG is kind of a graph representation of the control flow. So CFG actually does stand for control flow graph. If you look at the left-hand side, we have an if statement. A might be the head of the if statement, where you kind of encode the condition. And then B is the conditional block. C is where the control flow then merges back together. Or you can also have for loops. So this is not just a DAG, but it is something that has cycles. Yeah? So A and B has a cycle, but that could be a for loop where B is the loop body, and then when you go out, you move to C. Or on the right-hand side, you would have something that is like a for loop with a break in the middle. Yeah? That's kind of a CFG representation of that. Now we can mesh the two together and we get something like this. So if we take this Yul snippet where we have a variable x, we mload it, and then, I mean, this is kind of stupid code, right? But just for illustration purposes, we then check if x, then we set x to mload 42 and afterwards store it. And on the bottom half, you can see what the SSA CFG representation of that looks like. So we only assign variables once. And one thing that I wanted to highlight here, which is kind of special for SSA CFGs, is phi variables. That's what you can see here in block 2. In block 2, you have something that depends on the graph itself. So phi 0 will take the value v0 if the control flow stems from block 0, and v1 if the control flow stems from block 1. This is kind of how you can work around this problem of, I want to assign something and then it is constant, which otherwise doesn't really work. Right? If you have something that you set conditionally, you have to do something special. And that is that special trick to make the concept still work. Okay, we can also have loops, right? Then you get these back edges. I'm not going to go into that too much in the interest of time. And then we are pretty much ready to tackle codegen, right? How do we do codegen? So how do we take these SSA graphs and then transform them into EVM bytecode? This is the current pipeline of it. So we take a Yul dialect, which kind of is the internal representation of SOC saying, I have this and that EVM version, I'm in the context of Yul objects, or I'm in the context of inline assembly, and it takes an Yul AST, which could be optimized beforehand, which is something that we do right now, or it could also be unoptimized, which is fast, and then later on, once we have spent enough time on it, we can have optimizer passes in this SSA CFG IR and hopefully get away with a much better runtime. Based on that, we construct the SSA CFG, we make a liveness analysis, which is pretty much textbook. So that's kind of an a priori thing where you statically determine which variable is live when and for how long. I'll give you an example in a second. We also find bridges. I might actually skip over that a little bit. And then we have a stack layout generation pass, which transforms the SSA CFG based on the liveness and the bridges that I will skip to stack layouts. And then we have codegen. Okay, so what is liveness? And this is kind of the example that we had before, just a bit more complicated. And in these graphs, let's look at block 6. Right, that's like the second from the right. We have something that says live in, and then phi 3, and in what are these bracket codes? Angled brackets, I guess, 2. That means there is a variable phi 3 that is going into block 6. It is used either in block 6 or in one of its successors, and it is used at most twice. This is how to read this. And the live out similarly says phi 3 is going out of the block, so it has to stay live, as we would say, after finishing with this control flow block, and it only has a 1 now, so we know in difference phi 3 must have been used exactly once in block 6. And I mean, it is because that's the block where it is defined. Okay, and then we can do stack layout generation. And stack layout generation has kind of 2 phases. The first phase is inside of a block of code. Here it's a function block. You ask yourself, how does the EVM stack, right? The EVM is a stack machine. How does the EVM stack has to look symbolically at each step of the way so that I can execute whatever operations were implemented by the programmer that used Solidity or Yul, right? And the stack layout generation's job is to make that as efficient as possible. So here we have a function with 2 arguments, v1, v0, and so we know a priori for that function, if we call into that context, the top of the stack must look like v1, v0, otherwise we couldn't have called into it. And then we have an mload, and here you can see kind of on the left-hand side operations that are for preparing the stack for the next operation, and on the right-hand side we have the operations themselves. So for the first mload we don't need to prepare anything because we're just going to consume v0 and emit a v2. And then for the next operation, which is an mload of 42, we have to push the 42 onto stack. So the stack changes from v1, v0 to v1 and then v2, which is the result of the mload before, and then the 42. And then we can execute the next mload, which will give us v3. And then we have an add function. We need to swap it around, and then in the end we want to emit the v4 variable, or the value of the v4 variable. And for that we have to reduce the stack back to solely containing the v4. That means after the second to last line, we have to swap 1, which exchanges the stack top with the element beneath it, and remove that. That's the pop instruction. And this is then actually precisely what you would see in the EVM bytecode in the assembly. Yeah, that's how that is created. And now we also have funny things like if statements and loops and so on, and then we have to ask ourselves the question, what else do we need in order to properly stackify our code? And we also have to think about, if I have these function arguments, I might have code blocks, scoping, and then at these boundaries of blocks, I have to define what is the stack in and stack out. That's how we call it internally. That means it is the stack layout that I want to achieve when calling into a specific block of code or when I am leaving a specific block of code. This is kind of a global optimization problem then. Like, how do I define these points at these interfaces of the blocks so that I get the most efficient bytecode out? Yeah. And by using an SSA CFG IR, we can do that top-down, which means we can just look at operations, and we have a certain input stack, S, which is Sn to S1, and I probably should have mentioned that, but for me, mentally, the stack top is always on the right-hand side. That might be confusing for some. I'm sorry, I should have said that earlier. And then in order to prepare something for a target operation, what we have to take into account is, first of all, what are the operation arguments, right? And then what is live out after the operation? So what has to still be retained after the arguments of that operation have been consumed? And I also want to know what is the size of the target stack. And then based off that, I can devise very funny and complicated algorithms which are greedy and fast and are built on a bunch of heuristics, like down below. I'm not going to go into that because I just have 3.5 minutes now. But yeah, there's a lot of fun to be had with that. Doing it this top-down meta also enables us to attack stack to deep. Yeah? So stack to deep is the situation when I need to grab too deep into the stack to produce something up top that I otherwise couldn't reach. And in this operation forward shuffling, as I would call it, we can be sure that if we need to reach into the stack, then it is always due to one of the arguments. And this is where the SSA property rescues us, really, because the SSA property tells us, all right, I have this argument of the operation, and now I just have to trace worst case where it was defined. And I know at the point where it was defined, I can just put it into memory and then, mload it. And there we go. And this is like one way of dealing with it. It's a bit more nuanced, but I also don't want to take away too much from the next talk. So we're working on that. In comparison, right, I already mentioned we're going top-down. So we start with, for instance, the function head, and then top-down do the stackification. In the current viaIR pipeline, the approach is bottom-up, because there we don't have the SSA property, and we don't have explicit liveness. So what we do is we look at termination points, we look at function returns, and then bottom-up from these points kind of propagate the stack layout. And that also means that we see variables being used before they were defined, which is, maybe not the best way if you want to deal with stack to deep. With the SSA CFG, we get a top-down approach, we get explicit liveness, and we can also handle control flow joins more constructively. Meaning, if I have two blocks and I want to join them, so for instance, after an if statement where the conditional block is then producing something, then I can just pick one of the two stack layouts because I know already that all the information that I need is contained in either of them. This is like a very simple and constructive way and something that you can pretty easily bug fix. If you go bottom up, you have an information disparity. You don't necessarily have the property that both stacks or symbolic stacks contain enough information to do the join, and then I have to do more complicated algorithms, which are harder to maintain. All right, this is the bridge business, which we are going to skip. Then we want to stabilize the implementation, and to do that, we want to do a lot of fuzzing, right? We can do fuzzing in multiple ways. We can take Yul, we can optimize it, we can do codegen on that, and see whether the compiler crashes. That's maybe not very satisfactory. We can do better than that. We can also look at bytecode equivalence, for instance. And bytecode equivalence can be checked with the tools from our HEVM friends, right? Which is pretty nice. Or we can also just fuzz the bytecode itself by generating call data and then run the fuzzer on that. So that's kind of differential fuzzing then. And we can also draw from Sourcify, of course. All right, I have 3 seconds. I hope that's enough for the outlook. So status quo, we have a prototypical implementation of this new IR plus codegen. It's still a bit rough around the edges, but does its thing most of the time. And we are pretty confident we can release that into the wild relatively soon under an experimental flag. Next up would be then the stack to deep handling, so memory spilling. Right now, we already see in our tests that the bytecode performance, so gas used to deploy and run, is relatively on par with the current viaIR pipeline, which is a good sign, and sometimes even beats it. And because we don't really have the optimizer passes implemented yet in the SSA CFG IR, we can't really say how much faster we're going to be in the end. So it's kind of same at the moment, because we have to bring up these optimizer steps into the new IR that's pending. Yeah, that's it. Thanks.
Awesome. Thank you so much, Moritz. We've briefly mentioned the SSA CFG work in the past. So it was really cool to see the inner workings of it finally. We have a couple of questions. The first one, we've seen massive improvements from 10s of seconds to sub 1 second by just inlining all contracts into one file. Why do you think that is?
That might be something I have to benchmark. Like I could actually imagine that it is due to the function inliner, where I did see performance deficits in the past, but this is like highly specific. I would have to actually profile and benchmark this and see where it's coming from. So whoever asked this question, please let me know. Send me whatever files you're concerned with, and we can see whether we can figure something out.
Awesome. For compilation time, why not go towards incremental compilation?
That is something that we are exploring, but it requires some deeper changes to the IR pipeline right now, and this viaIR IR SSA CFG stuff is kind of an addendum, right? We can just switch it on or off, but it doesn't mess really with the internals yet. For incremental compilation, we have to do more changes, but it's something that we are actually considering also. Yeah.
And how does SSA deal with reallocation inside ifs?
With reallocation inside ifs. I mean, the reallocation would actually be a function of memory, or memory probably, and that's not really something that SSA form is concerned with at all. It is rather something that has to be respected by optimization passes, which do optimization over memory. So the SSA form then only really deals with the variables, stack variables, which point to memory locations.
Will the SSA layer allow inputs other than Yul?
Right now, no. Later, theoretically, sure. I mean, it's just going to be some IR that you can target and then generate code with it, right? So whoever wants to output it can use it and hopefully be happy with it. Yeah.
Okay. Has the recent increase in call data gas cost influenced any change on the compiler optimizer?
No, it hasn't. Like not in a deep sense. We haven't actually added any optimization passes on top of that, but that's something we can consider. Yeah.
Okay, and there are two questions that are quite similar. It's they ask, is the SSA CFG stuff included in core Solidity or classic Solidity?
Both. It's actually something that we can do for both, because classic Solidity targets Yul, which is the IR, and core Solidity also targets Yul. So yeah, win-win.
Okay, and we have just enough time for a last one. Given the SSA is on Yul, does it mean it does not support memory variable, like structs, etc.?
It doesn't have memory objects at the moment, but this is something that we are considering to extend Yul for. Yeah, so it's in the pipeline.
Amazing. Thanks for all of the questions that you answered, Moritz, and thanks also for the talk. Give it up for Moritz once again.
Thank you.